Having looked into all the properties of concrete, the production process and related issues, now we can look into how do we select material for concrete making. So, this lecture module 1, module 8 lecture 1 will discuss about cement aggregate and water selection, and therefore, obviously the outline of our discussion today would be, first we will discuss with cement selection, then we will have a discussion on water selection, aggregate selection, and that is it. Selection of cement. Ingredients of concrete are selected based on performance requirement of concrete. Like cement also we select based on what is the performance requirement of concrete, what we want from the concrete. And as we have mentioned earlier several times, performance of concrete in fresh state, that is this, hardening state, hardened state and long term performance are kept in mind. So, we select cement based on all this, because we have seen earlier when we looked into types of cement, then properties of cement or the cement itself can actually influence the properties of the concrete in terms of its setting, in terms of hardening, and then when it is hardened, and in the long term strength development and durability, etc., etc. Therefore, cement we select according to the need, as required, like as the performance we want from concrete, based on that requirement we select the cement, Okay. Well, the most common of course is ordinary Portland cement, that we have understood by now, and used in and it must satisfy of course the requirements of relevant code. There are 3 codes I have mentioned here. IS 269 meant for 33 grade, this is meant for 43 grade, and this is meant for 53 grade. Now, you see this obviously, as we have seen, this grade means that it will give you 33 MPa strength on 28 days when tested in the standard manner, cement mortar cubes. So, when we test standard cement mortar cube in a standard manner, then the strength we get would be getting 33 MPa here, 33. This is 43 MPa 28 days, and this is 53 MPa 28 days. Now, these 3 cements all are ordinary Portland cement. Obviously, you can understand that this gives a little bit of high 28 days strength cement itself, and here it is somewhere in between, and this is the least. So, obviously, how do you get it? If we recall, then possibly if you recall in the beginning we discussed about compounds of cement. C3S would gives you high early cement, C2S gives you long term strength, and if you grind it more, the physical fineness of the cement also enhances the early strength. So, that is what has been done here. Actually, you grind it more, increase the C3S content, reduce the C2S content compared to this, let us say, to get high strength, high early strength. So, there is no specific need where they should be used. In fact, any one of them is good enough, but if you think that 28 days strength, somewhat early strength you desire, this could be one thing, but it does not serve much of a purpose. Any one of them could be selected. This will have obviously long term strength, obviously this will have better compared to this, and when it comes to production of calcium hydroxide, this will have large amount of calcium hydroxide produced compared to this. The reason being this has got more C3S compared to C2S, and we know C3S produces more lime compared to C2S. Anyway, but there is no specific guidelines or specific places where one should use 53, when one should use 33. These two can be used everywhere, but this can also lead to high drying shrinkage and things like that. So, that is it, but you can get a little bit earlier. 28 days strength would be slightly more, and so will be 7 days strength, because 7 days strength is 2/3 of the 28 days strength. So, to that extent this will have some advantage, otherwise this does not have much of an advantage. Most commonly used are these days are 43, 33 was used earlier when nothing else was available. So, this is when it comes to the grade of cement, but then OPC is used everywhere most commonly. Well, today of course, use of OPC possibly in many small scale usage is reduced because of the availability of Portland pozzolana cement and mainly Portland pozzolana cement, fly ash blended cement. But most OPC you can use in most of the places. That is the first thing. OPC you can use in most of the places without any problem, and that is the most common. Right. Now, if I am looking at early age performance, then what kind of cement shall I select? This table tells you the cement selection, ideas of cement selection. For example, this column gives you performance required, this gives you cement type, this gives you an application example, and these are other effects, maybe side effects you can say. For example, if I want repair of runways, I mentioned, where you can't stop your traffic, or even roads sometimes where I can't stop my traffic, then the cement that I would be using should have the performance, that is, it should have very high early setting. And in such cases I use quick setting cement or the jet cement I mentioned earlier when we were discussing about type of cement, which sets very fast, So, if I require very high early setting, then I can use jet cement. That is an extraordinarily very high surface area, and you remember that even its raw materials are different, and it sets very fast. Similarly, quick setting cement, so they can set very fast, but they would generate heat of hydration. So, where only you require very early setting, you can't stop the traffic, the cost, they will be costlier, surely they will be costlier cement. In fact, this has to be imported. Now, where you need, where the extra expenditure is justified from the point of view of, let us say, traffic flow that you have stopped, because that would, if you stop traffic flow, especially in airport runways, it would mean huge loss to various organizations. So, if the additional cost is justified, then obviously one could go for this ones. So, where you need quick setting, very early setting, then you use this sort of cement. Some places you might need high early strength. For example, in precast element, because where you have prestressed or precast element, usually in prestressed concrete bridge construction, let us say, you have bridge girders which are prestressed. Now, they are actually cast in casting bed if it is post tension, pre-tension, they are cast in casting bed, and with the pre-tensioning wire tensioned in the beginning itself, and then cast the beam. Now, once the beam has attained sufficient strength, it can withstand some amount of compressive stresses due to the pre-stressing. You must release it, and you must release the bed as early as possible, because that would give you less cycle time, you can produce more at a faster rate. From economy, it is justified to release the bed as early as possible. Similarly, even in post tension system, where you have precast members, segments, say in case of bridges, now those ones you would like to release it as early as possible. The casting bed, you would like to release it as early as possible, because the next element you can start casting then. So, in such situation where you would like to get some high early strength, so that you can apply some load, the handling load, etc., there you need high early strength. So, precast element is one of them. Tunnel form construction of building, in tunnel form construction of building, you can possibly finish structural system of a floor in just about 3-4 days time. Now, what is done, you have a monolithic wall and slab construction, and the formwork can be shifted, it looks like tunnel, and it can be shifted from one floor to another very easily. Then through a crane, and then you pump the concrete in and quickly do the concreting and try to gain early strength, so that you can release the mold fast, because mold shifting process and fixing process is very short during that period of, in this type of tunnel form building construction, let us say. So, to get advantage, if you want to get advantage of this fast rate construction, you must also do your allow release of the mold as fast as possible. So, to do that one can use of course various means. You can use OPC with some admixture, RHPC rapid hardening Portland cement, or you can use OPC steam curing, heat curing, or any combination of them. So, my point is of course today's discussion is we are trying to select the cement. So, if I need high early strength, some examples I have given you, then I would possibly use the RHPC, or other solutions are also available or combinations are available. So, I can use all of them, but RHPC would be used in such situation. Rapid hardening Portland cement would be used in such situations where you know that I need high early strength. And obviously, we have seen earlier that if you get high early strength, this might have some effect on long term strength. You won't get as good as long term strength compared to OPC or some other cement. So, when I am interested in high early strength concrete, then I will be actually using rapid hardening Portland cement type 3, ASTM type 3, right. Still look at the same early age performance. Okay. If I am looking at higher workability, right, then cement alone may not do the job. That we have seen that cement alone may not do the job. We will use actually OPC plus admixture, right. This is useful for all application. As I said today, the modern engineered concrete construction cannot be thought of without some sort of workability enhancing plasticizer. This is workability enhancing plasticizer or admixtures, which are plasticizers or water reducing agent, and they are also called, they reduce the water demand, of the concrete for the same slump or same workability. So, one solution is used OPC with some sort of admixture. The other solution would be of course use OPC fly ash. As we shall see later on when we do mixed design, that fly ash can reduce some amount of water, and we discussed this earlier also in connection with use of pozzolanic material. So, when you have OPC with pozzolanic addition at site, there can be reduction in water demand. Of course, if it is pozzolana in the cement itself, then in any case you do not know whether a further reduction if you want, because it will have a given water reduction, further water reduction you want, then you have to use an admixture. So, you can have combination of all of them to reduce the water demand, and this has got application. Now, if you use only OPC plus fly ash, not for this, this is longer curing time would be, or formwork removal time will increase if you use fly ash combination. So, this is only true for FA, this is true only for FA plus OPC. This is only true for FA plus OPC situations where you might need a longer curing time. You have seen that you need 14 days instead of 10, and you need 10 instead of 7, where just OPC you can do it 7, here you would need curing time 10 days when you are using fly ash. So, curing time would be longer, and so will be the case with formwork removal, because strength gain is relatively less in this case, in the case of OPC and fly ash, and therefore you need a longer period of time before you could remove the formwork. So, this is the other effect. Then this is another case, low heat of hydration. This is required in mass concrete where you have thick raft, let us say, or in dam construction as we have discussed earlier. Many other places where heat of hydration is a problem, because if you have excessive heat of hydration, that heat would be locked inside the concrete, in the core of the concrete, because it may not be, depending upon the thickness, volume to surface area ratio of the concrete. In a thick section your volume is large, surface area is less. So, volume to surface area ratio is large. In such situation, evaporation rate from the surface is relatively slow, and all the heat from inside really do not get out. I mean, the cooling rate from the surface is slow, and all the heat from the core of the concrete is not dissipated in one go, it remains, and as a result there may be internal, it might be at higher temperature, the surface is at lower temperature, which would like to contract. So, when it is at thermal contraction will occur at the surface, where inside is still warm, and no contraction takes place. As a result, there will be a restraint to the surface contraction resulting in cracks. So, you would rather like that low heat of hydration. Here the heat generated itself is low, so that your dissipation process is low. Of course, you can have other means of cooling them and things like that, but the heat of hydration wherever it is a problem, especially mass concrete, thick raft or roads, pavement, etc., etc. In such cases, one option is use OPC plus fly ash, because we know the fly ash slows down the reaction. It will have, when you use OPC plus fly ash, some amount of OPC is replaced by fly ash, which means that there's heat of hydration will come only from OPC. Fly ash do not contribute so much to the heat of hydration, and in fact it will be initially not reacting till some calcium hydroxide is produced. So, there is a dilution effect, diluted, the OPC is now less. So, this results in less heat of hydration, because OPC, the heat of hydration is directly proportional to quantum of C3A present, C2S, C4AF and C3S present, mainly C3A, then C3S, etc. We have seen the amount of heat of hydration that comes out. So, mainly C3A. So, now quantity of C3A present in the cement you are reducing, so heat of hydration will get reduced, and fly ash do not contribute so much to the heat of hydration. You can have low heat Portland cement. This is IS 12600, low heat Portland cement. Essentially, it will have less grinding. It will be relatively coarser than, let us say, rapid hardening Portland cement or OPC, and we have seen the strength development of different cements. This will belong to actually type 4 ASTM cement, and it is just opposite to the rapid hardening cement. This does not harden so rapidly. So, its initial strength gain is lower, but heat of hydration is also lower. So, it will have more C2S component possibly than C3S component. Eventually, this would generate less heat of hydration, but you might require more curing, and then foam removal if you are using it in a situation where foam removal is required, but normally nobody will use them in such situations. They will be used mostly for mass concrete, where you do not require bottom shuttering to be removed, possibly it is onto the ground like thick raft and similar situations. So, or mass concrete situations. So, there you will be using this. So, this one has to keep in mind in case it is being used by chance, but normally in such situations bottom shuttering is not to be removed. So, usually because it will be on the ground, pavement, or let us say dam, or a thick raft that comes onto the ground straight away. So, but curing time required is long here, So, that is what is the early stage performances are we are talking about, right. Let us see the matured age performance. You remember we talked of maturity, matured when it has hardened, right, not the early stages, it has hardened, long term durability, strength, etc., etc. We are talking of them, talking of those ones. Now, if I if I just need the normal strength, then I can use OPC, even I can use PPC, etc. There is no problem, provided I know the rate of its behavior, which is known to us. So, high strength is desired. If it is high strength is desired, then usually it is preferred that a low C3A cement is used together with silica fume and then super plasticizer. This can be used for long span, tall structure, etc. High strength concrete, something like 100 MPa. You defined the high strength concrete, above 60 MPa we said is the high strength concrete. So, when you are looking for high strength concrete, say let us say above 100, below 100, instead of this you can even use fly ash and as an filler material and pozzolanic filler material, and use super plasticizer to reduce down the water cement ratio significantly. So, while you are trying to get high strength, the performance is high strength, OPC with preferably with low C3A component and silica fume and admixture, that is what is used. And this is, you see, the example is Petronas Tower in Malaysia, where they have used high strength concrete. In India, Kaiga atomic power plant, I think JJ hospital flyover in Mumbai, and there are several other structures which are where this is being now used. The nuclear power corporation, they used it first time I think in Kaiga. So, this high strength concrete above 60 MPa concrete, that there you can use these materials, and this can be used in very long span bridges or very tall structures, like I said Petronas Tower in Kuala Lumpur, that is one of the examples. Then we have seen this actually the sulphate resisting cement. So, where I want sulphate resistances, where where I am interested in sulphate resistance, then I would use OPC together with PPC, or preferably some cases OPC in low, you can even use OPC in low sulphate, but the code gives you IS 456 2000 gives you the details, right. You can use this also, but with certain additional thing, but then I can use PPC, Portland slag cement, and sulphate resisting cement, and in very high sulphate content I can use super sulphated cement, I can use super sulphated cement, I can use super sulphated cement. So, in sulphate environment, this one can use this, IS 456 2000 gives you the guideline. This guidelines for this is available in IS 456 2000, which at what sulphate concentration which of this to be used. At low sulphate concentration, of course, you can use OPC, and some cases super sulphated cement, some cases even maybe a coating or something onto the structure. So, depending upon the sulphate that you are encountering in the environment, one might select according to the select. And you remember the sulphate resistant cement is one where I will have less C3A content. Portland slag cement is one which is useful, and super sulphated cement is produced from blast furnace slag. We mentioned this sometime earlier, 85% blast furnace slag with OPC clinker and a little bit of gypsum. That is how we produce with super sulphated cement, which is a highly sulphate resisting cement. So, this is when you have sulphate resistance, sulphate required desired performance is that it should be able to resist sulphate, we can be using one of these cements. Seawater, again let us remember back, we talked about seawater situation, and in seawater we can use some cases we can use OPC, but PPC and PSC will perform better. Sulphate resisting cement is not the solution there, because you remember we talked about that sulphate resisting cement does not bind the chloride as much as possibly slag cement does. PPC and both by their virtue of their permeability, low permeability, they give you better structure, microstructure of the concrete, both PPC and PSC, and thereby they actually shows you improvement as far as durability is concerned. So, in seawater environment, one would possibly use any one of this cement, OPC also in certain cases, but then you will have certain additional things also, there are choices are many, but one can use PPC and PSC. So, that is what it is for selection on seawater. Long term strength, we have already seen that PPC and PSC actually improves the microstructure of concrete, the permeability reduces. So, one can use them. OPC also you can use, there is no problem, but you know the behavior of OPC. OPC will not perform as much as as good as PPC or PSC when it comes to long term durability, etc. But supposing I use PPC with slightly higher water cement ratio, OPC with lower water cement ratio will perform in the similar manner. So, I have choices available, I can choose from any one of them. The main important issue would be what is available, I mean easily available. If you have to, for example, if you have to, like Eastern Zone produces most of our slag cement. So, if you want to have small quantity of slag cement, let us say somewhere in the northern part of India, it is not very easy, right. It would take possibly time, the planning requires to be better. So, what is easily available, that is one can look into that, and with that one you can use judiciously, because if you know the behavior, then using it judiciously is possible. But certain things are, for example, almost not to be used, like sulphate resisting cement, let us say it is a costly cement. So, if you do not have a sulphate environment, why should you use it? So, that kind of judicious decision one has to take for selecting the cement, but the cost is a major factor. Cost is the major factor. Finally, one has to see what is the cost, and cost is economy, because you can't construct something without considering the economy. So that is how we do cement selection, specific cement selection. We go for cement selection in this manner. Let us say, let us look at the selection of water. Now, this is most important, because large part of our construction in the particularly in the northern part of the country, in let us say NCR region of Delhi, Rajasthan, UP and Haryana, there is far away from the coast, sea coast, and therefore the chloride induced corrosion should have been a rare phenomena here, coming most possibly occasionally, but it has been seen in housing sector. There is a large amount of chloride induced corrosion in these areas too, in buildings. If you remember, if you can recall the photograph that I showed with reference to corrosion, when we are talking about durability of concrete, a slab whose bottom was totally, the concrete has spalled off from the bottom completely. Now, if you recall that photograph, this was not for, the reason was actually high chloride content. Now, where does the chloride comes from? It comes from the ingredients of concrete in such situation. In fact, you can understand, you can find out whether such chloride comes from ingredient or whether they are coming from the outside. You can find out. For example, if I determine chloride in the concrete surface. Now, if the chloride is coming from the ingredients, then supposing I take a sample from here, take a sample, and this core sample I have taken out, and I measure the chloride in this, I slice it off, measure the chloride here, chloride size, slice it off and measure the chloride for each of these slices, this slice, this slice, this slice, etc., etc. Now, I will find the profile of the chloride. If it is coming from outside, profile of the chloride will be something like this, It will be maximum here and less on the other side. But if it is coming from the ingredients, you will find more or less similar chloride, uniform chloride. The distribution of the chloride will be uniform throughout. So, this is the chloride from inside, internal chloride. If it is internal chloride, it will be something like this. This will be the distribution. If it is external chloride, this will be the distribution. So, this is external chloride, external, right. So, one can actually find out whether the chloride has come from inside or from outside. Now, by and large, if you see the places, the buildings, particularly buildings, its infrastructure, this problem is not so much, because you have better quality control. You at least, you must be testing the, one has to test the water quality. But housing sector, this is relatively a problem where construction is not fully engineered. One would call, like if you have a sort of wave batching converted into a volumetric batching, and then mixing by simply rotary drum mixer, and that's not fully engineered concrete, and then water is just mixed without real full control. In such situations, quite often it has been observed that contamination in water contamination, the chloride comes into concrete through water. And how does it comes from? Because water used in most of these North Indian places, is groundwater for construction. So, when somebody is using groundwater, deep groundwater source, this could contain a lot of salts, soluble chloride salts. River water will not have, because all chloride soluble water would go away. So, contamination in terms of salt concentration high if you go deeper and deeper into the ground, and this is, supposing this is used without testing, quite often you may have a lot of contaminants in it, and it can result in long term durability problem and other problems too. Now, let us see. So, first thing is contamination shall not be, should not be there, and if it is there, what are contaminants? Contaminants are there, those ones which hinders the hydration process or interferes with the hydration process. So, one issue could be contaminant presence in water, it should not hinder the hydration process. For example, if supposing there is a sugar factory and the sugar factory's discharge, sugar water discharge goes into the ground there, and somebody is using into a pond or some such places, let us say, and somebody using this water for concrete making, obviously concrete is not going to set, because sugar is known to be a retarder. Just as an example, sugar is a retarder. So contaminants, supposing a little bit of sugar comes from the sugar factory or molasses or something like that, goes into the water that you are using for concrete making, it may not set properly. So contamination, because sugar interferes with the hydration process. So contaminants should not interfere with the hydration process, that is number one. It should not interfere with the hydration process, this is number one. Number two, it should not induce long term durability problem. The earlier example that I have given, the example that I have given is of chloride. Now due to reinforcement corrosion due to chloride, that is reinforcement corrosion due to chloride. Now that is a long term durability problem. Now the contaminant had actually induced a long term durability problem. Whereas if I have some sort of sugar coming as a contaminant into the water, the extreme case of course, this means that it will interfere with the hydration process, it will interfere with the hydration process. So neither the contaminants in water should not do both, neither it should do this or that. Also it should not have too much of alkali content, which may lead to actually maybe help in alkali aggregate reaction, although that is not very well known, but such alkalis which can react with some of those silica present in the aggregate. So those are the issues, contaminants should not be there. Right. So what is done? The code we will discuss, the code has given us, we will discuss that the code has given us guidelines, what should be the best sort of water which will not actually lead to either of this problem or problem of long term durability or problem of hindrance with the hydration process, slowing down or interfering with in some manner. So the code has given us guideline that how to tackle this. So it has given us the range of contaminants that is permissible in water, that we will discuss. But in some cases it may happen that you are a little bit doubtful, because you have not been able to, you have tested and you are not able to test properly, and you are doubtful that it might actually hinder the process of hydration. So in such cases, two tests has been proposed by the code. One is with reference to setting, the contaminants present in water should not disturb the setting process. So one is with respect to setting and the other is with respect to strength development. So it is suggested that in case you have some doubt, regarding development of strength, you can cast cubes with the proposed water and distilled water and you can compare them. Simple, because where you have doubt, so best thing is to do what? Well, take the most suitable water, that is distilled water, and use the proposed water and compare the cube strength results. Let us see what we compare. We actually compared 28 days cube compressive strength. And strength of concrete cast with proposed water and that with the distilled water. And the 28-day strength should not be, should not be distilled water, this should be more than 90% of the distilled water. It should not be less than, in fact this is less than, should not be less than 90% of that cast with distilled water. It should be greater than 90% of that cast with distilled water. So that is the idea. So that is the idea, So if it is coming 90%, then we are not really worried about, but if it is coming, that is, if I say F C proposed water of 3 samples etc., proposed water, this should be greater than 90%, greater than equals to 90% of Fc 0.9, 90 I mean 0.09, I will say 0.90 Fc of distilled water, and then we can accept this, then we can accept this water, then we can accept this water, otherwise we can't accept. So, that is the idea. Then initial setting time, we also test the initial setting time with proposed water and shall not be less than 30 minutes. Obviously, then you have a problem. If it is less than 30 minutes, then you have a little bit of problem. If it is less than 30 minutes, then we have problem, because you see the setting time should not be, in any case should not be more less than 30 minutes and shall not differ by plus minus 30 minutes from that of paste prepared with distilled water. So, you prepare distilled water, measure their initial setting time, and initial setting time in no case should be less than 30 minutes, because that is the minimum requirement for any cement, and this also shall not differ by 30 minutes from that of paste prepared with distilled water. For example, if you get with the distilled water, let us say you get 60 minutes or let us say just 30 minutes. Now, you should not get like the difference should be between, and this you get let us say 90 minutes. So, 90-30, this difference is too large. So, that is what is the point. The difference between the two should not be also plus minus 30 minutes from that of paste prepared, because then it is disturbing the setting process, may disturb even the hydration process and hardening process, etc., etc. So, these are the two tests required. Now, let us see what are the guidelines given. The code gives us a guideline that pH should be less than 6, pH should be less than 6, that is the guideline given in code. But it is generally said that pH should be between 8 and 6, it should not be too alkaline, it should not be too acidic, because in such acidic environment the reaction process may not progress in the right way. The chemistry of course is not really of our, I mean we do not really need to go into the chemistry of it, how cement reacts, the mechanism, but at a pH between the reaction proceeds properly in a neutral environment. In high alkaline or low alkaline or high acidity acid condition, the reaction do not go properly. Also they might also impart to in the, I mean basically impart or induce some durability problem in future. So, that is why the pH, suggested pH in the code is that it should not be less than 6, but additionally we say that it should not be greater than 8 either, and that is why the code has given you tests, and these tests are, for example, for 100 milliliter of water you need the sodium hydroxide 0.02 normal, you need you take 100 milliliter of water, the amount of sodium hydroxide needed to neutralize this 100 milliliter of water, we use 0.02 normal sodium hydroxide solution, and this should not be more than 5 milliliter. If it is more than 5 milliliter, that means that is more acidic than we really, because this will contain some acidic material, dissolved acidic material, and this is neutralized by sodium hydroxide. So, if I should not require more than 5 milliliter of sodium hydroxide of strength 0 to normality to distill neutralize 100 milliliter of water. So, that if it is more than this, it means that it is more acidic, then I require really want, and that is not desirable. Similarly, for alkalinity I have a test, and this test is 100 milliliter of water when I am trying to neutralize with sulfuric acid 0 to normal strength, sulfuric acid 0 to normal strength, then I should not require more than 25 milliliter. So, the amount of 0 to normal sulfuric acid required for neutralization should be less than 25 milliliter. That means it is properly alkaline. So, these are the two tests adopted in the code to ensure that it is really not as too much acidic nor highly alkaline, it is within the bounds, and this is to test. In addition, other prescription those are given or other recommendation, the organic solid should be less than 200 milligrams per liter, should be less than 200 milligrams per liter, 200 ppm, because milligram per liter would mean also ppm, parts per PA. million. I mean, inorganic solids 3000 milligram per liter. Now, this is important, SO3 sulfates 400 milligram per liter, although you know sulfate in fresh state really does not create any problem, because sulfate in the fresh state is not problematic if it is only if it is too high, because SO4 in gypsum in the initial phase actually reacts with C3A, but excess sulfate has got no meaning. So, therefore, there is a control on the sulfate as well. But most important I would say is this aspect, the chloride, most aspect is chloride, and you see these values are restricted to 500 milligram per liter for reinforced concrete and 2000 milligram per liter for plain concrete. So, this is most important, this is the most important, because this can induce rebar corrosion. Just this, and in addition to this, if you also remember that we said that the total chloride present in the concrete should not be some value, certain kg per meter cube of concrete, we said 0.6 kg or whatever it is we just mentioned earlier overall, but at the same time water should not have this. So, this there is another bound, water should not have too much of chloride, total chloride, some more chloride might come from aggregate, etc., etc. So, this is the most important part, because chloride presence can really create problem in long term durability. So, that is these are the requirements as far as water is concerned. As far as water is concerned, curing water suitable for mixing is suitable for curing as well, it is suitable for curing as well, but one has to ensure that curing water does not produce any stain. Same problem, curing water of course will not affect the initial hydration process, but it can surely affect the long term durability. So, you can't use chloride contaminated or sulfate contaminated water for curing. So, water suitable for mixing is also suitable for curing purposes, and one additional feature is very much there, that it should not produce any stain, no color, because if there is some some amount of iron present, soluble iron salt is present, then it is permissible as far as the previous recommendation of the code is concerned, IS 456/2000, but it might give you a red colored stain. So, that may not be aesthetically acceptable, that may not be aesthetically acceptable. So, therefore, one has to take additional care that it is not aesthetically, it does not create any stain as far as curing water is concerned. I have already mentioned that excess carbon dioxide or chloride which can attack the concrete, they should not be present in curing water, they should not be present in curing water. One important issue is this, is normally it is said a potable water which is fit for drinking is also fit for construction or concrete mixing. Well, by and large this is true, because bacteria although affect human being, it does not affect the concrete. By and large it is true, but more importantly the guidelines that has been just stated or given in the code, one has to follow the code actually. This is only some excerpts from the code to give you the understanding of how one should go on selecting the water and what is the importance of water, proper quality water in concrete construction. So, one has to go by the code. Although loosely speaking people say potable water, if it is fit for drinking it is also fit for mixing, but that is may not be always true. Second issue is of course the sea water. Well, sea water should not be used, preferably not to be used without treating, but if you are you have no other way, you have no water, you have to use that water, then you have got to take adequate precautions, because then you are risking your concrete, you have already embedded some sort of a kind of a germ into the concrete, a contaminant into the concrete right in the beginning. So, therefore, one has to take care of this aspect. That means, you should see that it remains free of water during its service period, should not come in contact with water, etc., etc. There can be more than one solution possible, but one has to be careful. So, sea water is not debarred fully, because if nothing is available, what to do? But you must test the water whatever is available, right. There may be difficulty that we have no water available. So, what to do? Well, whatever is available you test it and accordingly take right kind of precaution right kind of precaution. I mean, if you can't treat it, treatment may be very costly. So, accordingly then you take right kind of precautions, that is the idea, right. So, that is how we go about selection of water. Let us see how we go about selecting aggregate. First thing is, aggregate should be satisfying the requirements of IS 383, which is the code meant for which is the code meant for aggregate. So, we will say a coarse aggregate or fine aggregate, it should satisfy the requirements of IS 383, that is the first requirement. Let us see what are the specific requirements that we are talking about. Well, if you remember, packing characteristics of aggregate is most important. Therefore, grading is important because we got to control the packing characteristics. And as I said that we do not have really a model whereby by finding out proportions of various components of the aggregate, various sizes in the aggregate, I am able to find out what is my packing density, what maximize or gives me the optimal packing density which I require. Since we did not have that kind of packing models available, and even now there is only in literature, not in codes. So, most of the codes gives you boundaries of grading, the zones or ranges of grading, which I think I have shown you sometime earlier. So, aggregate gradings ranges are usually given, some ideas I would have given you earlier, but you can also understand the fact that IS 383 gives you such guidelines, the ranges of the aggregate permissible range zone, what are the permissible ranges of sizes, various sizes, proportions of the sizes, allowable sizes, that is what is the grading, and it is important. Now, if you do not have the graded, for example, if you are mixing two different sizes, you can mix them the proportion in right proportion to get the overall grading. This is very easy, this is not a it's not a very complex job. One can find out, supposing you have a binary mixture consisting of two x1 of one particular size and x2 of other particular size, then what should be the proportions in the overall aggregate system, because we know the proportion of one side should be between, let us say, 90 to 100, another should be from, let us say, 75 to 95 and so on. So, knowing the proportions that is required, if I know how much of these two I am mixing and the proportion of each of the aggregate sizes in this one and this two, I can actually, simple arithmetic, one can find out how one can satisfy the grading. Okay. So, grading it must satisfy, and you can mix up aggregates from different cohorts, let us say, or different size aggregates to get the right kind of grading. Fine aggregate to coarse aggregate proportions, one of course decide through mixed design, right. So, grading is most important parameter one has to look into. Then aggregate is selected from the point of view of strength and durability. You can't select any aggregate, you got to select such aggregates which will satisfy the requirement of strength and durability. Durability means alkali aggregate reaction one has to look into, and from strength it should have sufficient strength. It may not be very strong, but it has to have sufficient strength, and we measure this strength by what is called not direct strength measurement we do not do, we measure it through what is called aggregate crushing value. Now, this aggregate crushing value is nothing, you take specific amount of aggregate passing through particular sieve and retained on a particular sieve, then crush it in a standard manner, like something like applying 40 tons load in 10 minutes or so on with a specific rate of loading. Now, when you crush these aggregates, crush the aggregates, then some powders will be formed. So, sieve it through say 2.36 millimeter sieve, the percentage passing through that is an indication how much has been crushed. More crushed means it is weaker. So, we actually make a relative kind of test on aggregates, things like aggregate crushing value test, and it must have a minimum value or it must have a maximum value to be selected as suitable for structural concrete. So, usually it is not a big thing. Most of the used aggregates are used, whichever you already are in use, this aggregate satisfy the requirement of crushing value requirement. So, that is one issue, the strength should be sufficient. You just can't pick up, let us say, broken brick pieces and put it in the aggregate, that will bring down the strength of the normal strength concrete. We are talking of normal strength concrete at the moment, right. Maximum of size of aggregate MSA, nominal MSA we talked about. MSA shall be maximum possible, because it will improve the packing. So, as much as possible MSA I should like to use, because that will improve the packing. You remember we talked of the more the number of sizes, more the number of sizes, I will have better packing. Single size packs do not pack so well, 2 sizes will pack better, and more the number of sizes I will have better packing. And we also said that higher MSA would improve my, it reduce down my water requirement for mixing water for a given slump. You remember that when we talked about aggregate earlier, when we talked about we mentioned about this. Something more, we also discussed the strength. When we are discussing about strength effect, we said that MSA, higher MSA is suitable for leaner mixes, and smaller MSA is required for rich mixes or high strength mixes. So, if we look from that point of view, strength of the concrete reduces as MSA increases, as I increase the MSA. So, we have seen that 150 75 MSA for uses for mass concrete, and 20 to 40 millimeter MSA is usually suitable for structural concrete, and 10 millimeter for high strength concrete or fiber reinforced concrete, because the fibers spacing is related to the size of the aggregate, workability of the fiber concrete, fiber reinforced concrete is related to the size of the aggregate. So, this is rough guideline. Normal strength concrete is use maximum MSA 20 millimeter or 40 millimeter, usually 20 millimeter. 40 millimeters aggregate, if it is available, we might use, and it is suitable, but this is roughly the idea. So, MSA is selected depending upon actually strength and also on the and largest size I like to use. But one more issue is related to the aspect of the structural element itself, that is the maximum MSA should be cover minus 5 millimeter, because it has to go between the steel bar and the shuttering. So, it should be less than cover minus 5 millimeter or bar spacing minus 5 millimeter. This should have been a bracket here, bar spacing minus 5 millimeter, whichever is lower. So, MSA cannot be maximum MSA you use shall be lesser than this. So, this is the practical construction criteria which governs in addition to the above criteria. So, you select aggregate according to maximum size of the aggregate according to this, but remember higher the MSA, lesser will be your water requirement. So, you try to find out an optimal from consideration of this, whatever is maximum possible, you use that. Both natural rounded gravel or crushed aggregate can be used, and they are used effectively. You know the behavior, then there is no problem, because we know that rounded gravel, it would reduce down my water requirement significantly. But if its surface characteristics such that it is not porous, it is not rough, it can reduce down the bond strength a little bit, right. So, if smooth surface of the natural gravel, if it is there, then that can reduce down the bond strength. But this might be adequately compensated due to the fact that you will have significant amount of reduction in water content, water demand for the concrete. Crushed aggregate on the other hand, well, but natural ground gravel may not be available. I mean, finally, it is availability, because you can't, supposing you are constructing something in say Chandigarh, you can't get your aggregate from Chennai, that is not possible, even though that might be the best one for your purpose. So, that is not the thing, that is never done. Wherever you have the construction, you try to get the nearest aggregates possible, because of the cost, and it is a natural material mostly, you just process a little bit, at best you crush it. So, crushed aggregates locally available, if it is sufficiently strong, you know that it is not potentially prone to alkali aggregate reaction, then you can use this crushed aggregate. So, usually one uses crushed aggregate or natural gravel, whatever is easily available, Special cases, if you have radiation shield, you know like for example nuclear reactor, now its wall, it needs radiation shielding, you do not want radiation to come out of it. In such situation you use heavy aggregate, right, something like magnetite or hematite, very heavy aggregate, density is very high, because it is the high density and the thickness, of course, high density is required to absorb the radiation, not allowing the radiation to go, and this concrete we call heavy concrete. This concrete is known as heavy concrete. This concrete is known as heavy concrete. So, when you have heavy concrete, heavy density aggregates are used. In very tall buildings, right, in very tall buildings the wall does not carry any load, it is the frame structures, whatever way it is, so they take the load. So, the envelope, the actually the closing is, this envelope is closed, the space is closed by the walls. So, wall serves the purpose of the envelope, and it does not have to take load, it has to actually withstand its self load and any horizontal load, horizontal local wind load, it should not itself collapse. So, it has to withstand transverse loading and some sort of self load, that is all the load it has to take. So, load is not an important criteria in very tall buildings, the walls are not meant for carrying loads. In other even 5-6 story buildings, many cases wall might simply act as enclosure and nothing else, but wall has got other functions to do. It may require, we might require thermal insulation and acoustic insulation, and in such cases lightweight aggregate does the job, because thermal conductivity is an important parameter, and lightweight aggregate, when you use them, if they are natural or synthetic aggregate could be there produced from, let us say, fly ash or slag or similar sort of thing, or various aggregates, those are produced by sintering processes, right. These are, they are chosen because of their thermal and acoustic properties and not much from the load carrying point of view. So, that is it, that is how we select aggregate. Synthetic aggregate from fly ash and slag can also be used for non-structural purpose, but they can take some structural load as well, they can take some structural load as well. So, but there will be less, but load bearing wall of course you need, right, but load bearing wall, if it is concrete monolithic wall, as in case of tunnel form construction, now that requires strength also, right. Here the wall itself is monolithic to the slab, and it carries the load from the slab is transferred to the wall and next to the next level and so on and so forth. So, there the strength is required, where strength is not necessary you can use lightweight aggregate. Yes, this is most important, the alkali aggregate reaction potential and other durability considerations are primal. So, when it comes to aggregate selection, these are the primal issues. I think we have discussed most of it, aggregate selection earlier itself when we were talking of properties of concrete. So, now that we know it, so only we are compiling them back again, re-looking into them while selecting cement or selecting aggregate. The water, of course, we did not look much into water quality. So, that is what we are doing, right. Now, one important issue is that when you look at sustainable concrete in future, not in this country at the moment we are not really using recycled aggregate, but aggregate resources are not infinite, and hence you can't go on using the natural aggregates. So, this concepts of recycled aggregate is gaining popularity somewhere elsewhere in the world, and one may think in this direction as well, right. Recycled aggregate is popular, not yet, and on the other hand, because the building you have to demolish after 30-40 years for various reasons, because it must have done away with what is known as functional life. So, in such situation you demolish this debris, what do? You have to actually do, it's another kind of environmental problem. So, you try to recycle them and use them in construction again. Admixture, most important when we are selecting admixtures, it should be compatible with the concrete, and its all solid content etc. requirement should be seen as per IS 9103 code. Shall not contain any material harmful to concrete durability, that is important, but the effectiveness are determined only through trials at site, there is no other way you can do it. Admixture, finally its compatibility, whether it has got any side effect or not, that has to be tested with the concrete that you are using. So, once tested, once you are satisfied, then you can use it. So, there are various, because these are all commercial product, the branded product, the commercial product, and then you have to test them to actually see their compatibility. What might be compatible with one particular cement may not be compatible with another cement. So, this is an important issue selection is based on systematic procedure of testing and nothing else. So, one has to go by testing. In fact, there are compatibility tests for high strength concrete, tests called Marsh cone test, flowability test is done, then there are mini slump tests and so on. There are several tests for testing compatibility of admixtures. Finally, you do the test, see whether it is actually reducing your water demand or not, and does it have any side effect or not, and then only you use it. So, that is how we select materials for concrete construction. Well, so what we have seen so far? We have seen cement selection. How do you go about selecting cement? Then we have also seen how do you select water, the contaminants in water, and lastly we have looked into aggregate selection and admixture selection. So, that is the first step in concrete making, you select it, but once you have decided, then next step is of course is to go for designing the mix, and that is it. Okay, I think this summarizes our discussion on concrete material selection. Thank you.